It's based on random trees, and we need to perform bugging to the dataset and some other stuff also.
Not exactly. The first thing is that basically we don't have to take trees to construct gradient boosting. It's just the most common way. So the main idea to have many models and to perform training with the first one, and then we calculate the derivative of the loss function, and then we use this information to train the other one. So this is the basic idea of this. And the most popular way to create such type of algorithm is to use trees. So, okay, then let's talk about trees. How do you think, what is better, having deeper trees for this kind of algorithm, or more shallow?
Not deeper, so more shallow.
And why?
Because it might take too many steps, and also might be very specific to the data set, I think. So it can overfit.
Yes, this really is true. And the other thing is that the trees are made up the way the most important features are always in the top of the tree, closer to the root. So basically, we just use the most shallow ones to capture the main features, the main dependencies of the data set, and avoid overtraining. Yes, so you're right. Okay, and tell me, please, how is the tree built? Just if we consider one tree without any random forest or something like this.
We use some predicates to classify our data.
Yes, basically yes. And can you name one loss function that we can use for this?
For random trees.
For any trees.
I forgot the name. It was one very popular.
What? Sorry. Can you repeat, please?
I forgot the name. It was about measuring how the complexity of the tree, or
Well, not the complexity. You see, when we make up a tree, we try to capture some connections between the features and the targets of our data set. So we separate our objects in some way, and we want it to be somehow well organized. So there is a criterion which has some link to some physics, which measures the um, the state of chaosity of our objects in our tree. So how is this called?
Oh, it's entropy.
Yeah, this is entropy, and entropy criterion. And also there is a Gini criterion, which is very similar. Um, okay. Okay, there are several frameworks which are Catboost, LightGBM, XGBoost, and all of them used to have their specific way to build the trees for boosting algorithms, but over the time that has passed, they have exchanged their algorithms, I guess, in some natural way. Basically, you can choose many policies of creating trees in each of those um, frameworks, and today we'll talk about Catboost first, and then the other one. So, okay, as you can see, we have Titanic data set, and we have lots of texts and lots of and we can see that there are some missing values. So what are your suggestions about what to do about text and missing values? What we can do? Okay, let's start with missing values. What can we do? What can we possibly do with this?
We could assign by default the mean of each column feature, and
Uh,
then,
well, not bad. And something else?
well, and then we should correct this value, like depending on, no, after.
Okay. So let's think that we are building trees. So um, possibly we would like to group all those objects with missing values of some feature altogether. Guys, is this a good idea or not?
How do you make software?
So we can assign something which is very far from other values for this column. So we will just get rid of those objects, but they will still be somewhere, and we will use the existing part of data from those objects. Is this a good idea or not? So basically, what's the difference? You um just said that it would be okay if we calculate the mean or some default some default value and just fill in the gaps. So what I'm saying that we can assign the missing value to some very unusual for this feature value, and this would help us use every other feature for those objects. But then when it comes to the feature with the missing value, we would group all the all the objects with the missing value in one place. So is this a good idea? According to the fact that we are building trees.
Well, it doesn't seem very bad because we're not considering those missing values. But what if we have no data with no missing values? How could we construct our trees in that case?
If we don't have any data without or with missing values,
We have no data that is completely like
which
without.
is complete. Well, if you have some feature which is absolutely incomplete along the whole data set, maybe you should consider not using this feature. Or doing something else, like, I don't know, separating the part with this feature with present values and with the absent. But if you have just sparse data, like somewhere you miss one value for one feature and the other place and the other object misses another feature, so you just can work with this just the way we talked about it right now, by assigning something very, very far from the default value, or just assigning the mean or something like this. Okay, and what about words or something like this? What would you normally do if you were using some if you were doing this by yourself, not with some clever framework which would do a lot of work for you?
A decision tree, how we would construct,
Uh, well, in decision
or
tree,
what is the question?
so the question was that there are some textual features, like name or something like this. And normally you would like to transfer such features somehow for it to be easier to work with. So how could you possibly transform textual features?
Uh, I would assign to what do I map into, I don't know, natural numbers, and every some number represents some name, like something like that. And maybe if the order matters, or I don't know, like handle that also.
Maybe some hash function will help.
No, yes, it's this question doesn't have one exact answer. It's just you can do whatever you want to do, as far as it has some mathematical idea, and as far as it transfers the textual features into something that you can easily analyze and manipulate. Okay, so here we just check how many missing values do we have, and then we place the missing values with something which is exactly we're just completely sure out of the distribution. Okay. Okay, what about Catboost? Catboost is very popular and convenient way to perform gradient boosting. There is also Scalor, but it's I'd say it's just for exercising and experimenting with this when you're still learning how does it work. And such frameworks as Catboost and others are more for production and real life applications. Okay, here we create a model, and we select the loss. So and obviously this is a metric which I think would be our target one. So let's discuss, is it okay to have accuracy for this data set, and what are the flaws of accuracy? So the first question, for which data sets it's great to use accuracy as a metric?
Maybe when we're not where it's not classification like yes or no, but with continuous value.
Well, the main idea is okay, if we stay in terms of classification, there is something about the data set that you have to make sure of to use accuracy, and don't worry about this, and not to worry about this. So what it is? Okay, what classification metrics do you know? The most common ones. Okay, I was talking about the metrics. So obviously not naive bias. I was talking about precision, recall, F1 score, accuracy, error rate, and so on. So what's the difference between F1 score, precision, recall, and accuracy and error rate. Okay, what is accuracy? Can anyone tell me how can we calculate accuracy? For example, we have a data set with we have a data set of fruits, and the 90% of fruits are oranges and 10% are apples. So what would be the accuracy of constant prediction of oranges?
It would be the number of oranges our model, no, our model said it was orange over the actual value.
So it would be how many percent? If we have 90% of oranges in the data set, we always predict oranges. So what would be the accuracy? If accuracy is the number of correctly predicted predicted objects divided by the total number of objects, so this would be
0.9.
yes, 0.9. So in percent, it would be 90%. Yes. So this situation may make you remember the problem about the accuracy. So the data set was imbalanced, and that's why the dump model, which predicts always the same prediction, has 90% accuracy, but this is extremely bad. So if we have imbalanced classes, we use which matrix? Guys, have you heard about precision and recall? Okay, we use precision and recall, and also F1 score. And these are the most popular ways to estimate the classifier in case of an imbalanced data set. Okay? Please remember this. I guess you will have to learn it for your exam. Okay. Unfortunately, the plotting for Catboost doesn't work in Collab, so we are not going to see this. Okay, and now we start cross-validation. What is cross-validation? What is the main idea of it? Can someone tell me, please?
It's we used to validate our model, in which we divide our data into groups, and we iterate over our validation set.
And how do you calculate the final result?
It's the mean.
Yes, yes. Okay. So we have quite nice score, but it's still accuracy. So we don't really know how good is this, because we don't know about the imbalance, if the data set is imbalanced or not. Okay. There's also such thing as pool, which stores lots of information, and it's quite convenient to use this one. Okay. There is also early stopping. Early stopping, I guess. I guess it saves time, but if you have your trees correctly configured, it won't take that much time to train the gradient boosting. It's not deep learning when you can spend days waiting for your model to study. Okay. There is also such thing as baselines, which you can use with this framework. Well, I guess it's not. It doesn't make that much sense to me, because I generally do deep learning, and I understand how important it is in deep learning, because um, it may take a lot of time to a deep learning model to converge, but I guess in Catboost and in boosting generally, it can be also very helpful for something. And you also can create your custom objective functions. And you can also take a look on which features are more important, considering your model. So here we see that feature sex, class, ticket, and cabin are more important, and the others one are not that much. And it's obvious that passenger ID and name have zero importance. And well, it's quite logical, because passenger ID is like ID of a name, and name doesn't influence. I guess it doesn't influence somehow the fact if the person survived or not. Okay, here we move on to evaluation metrics, and here we have area under curve. So please tell me how is this one calculated, and well, and tell me about a rock oak curve. How is this? How is it? How can you draw one? Okay. Okay. The first question: what are the axes to draw a rock oak curve? Guys, someone, anyone?
Can you repeat the question? I didn't get it. What are the axes for a curve?
What are the axes we use to draw a rock oak curve?
To draw a what?
Rock oak curve.
Rock owl curve. Sorry, I don't understand. What kind of curve?
Okay, I'll write this in the chat.
Thanks.
I may not pronounce it correctly because okay, I have strong Russian accent, guys.
Like the false positive rate.
Yes, and
What was it? There will be the false positive rate on the x-axis and the true positive rate, right?
yes,
I
exactly.
think.
Okay, so how do we draw this curve?
Like which library to use?
No, okay, you have some objects, and you predict probabilities for them to be of certain class. So, for example, object 1 has probability 0.6, object 2 has probability 0.5, and object 3 has probability 0.1.
Okay.
So how would you draw a Roca-Hook curve for those objects?
They have these probabilities that we are correct.
Okay.
But we need
Let's say that we predict probabilities from 0 to 1, and 0 is and having probability closer to 0. This means that we predict this is the 0 class, and closer to 1 it would be the class marked as 1. So let's just pretend that we have a threshold.
Okay.
Which is 0.5, and everything which is lower than 0.5 we consider being class 0, and everything that is greater you can consider being class 1. So you have 3 objects. One is 1.6. The second is 0.6, 0.5, and 0.1.
Okay, and we want to draw the curve.
Yeah.
And so there's only 2 classification, right? Below 0.
Yeah, this would be binary.
Okay. And we don't know the original classes of the data. We don't know the distribution.
Let's say that the first one is class 1, the second one is class 1, and the third one is class 1.
So I think we can just directly calculate the false positive rate, just see which we got wrong.
So, for example, you want to draw for example, you want to draw a curve only for one threshold, not for all thresholds, but for one and only.
Okay. Yeah, so we just calculate it will be just our mistakes, right? Just false positivity rate and true positivity rate. Like the first one was 0.1, and it was the first one.
0.1, yes.
So it will be like, we'll consider it in the correct that we guessed it correctly. Same for the second one, I think. And the third one we guessed wrong, right?
Yes.
Yeah, so the false positive rate was 1/3 here. Right? Unless I'm misunderstanding something.
How much?
1/3, because we got one wrong only.
Yes.
Yeah, and the true positive rate would just be 2/3.
Yes.
Okay, so we got the values.
Okay, we have the values. And so what about the area on the curve?
Oh. Let me think. Wait. Sorry, 1 second.
Okay, I guess we'll have some discussion about this later. Because this is an important question, and I guess you will have something like this in your exam, and you actually should understand this.
Okay.
Okay.
Yeah.
Now for now it's absolutely okay. I'm just marking for myself what should I tell you sometime next time. Okay. Okay, there is also an integration with some automatic parameter tuning for Catboost. For example, with HyperOpt. HyperOpt is a very it's a very widespread framework for such things. So we will take a look how it works, and it works without any additional effort. I mean, just you to take a look at the docs, and you will probably understand how to start hyperparameter tuning without any difficulties. And it's really cool because really there were times when we had to write all such things like a grid searcher or something like this ourselves, and such integrations are very, very convenient. So let's take a look how much time it would take and what would be the results. So as it is training and optimizing, let's discuss the learning rate. What is it? And why is it so important for all the gradients algorithms? Guys,
It's the step size like we use for each iteration of our optimization.
yes, that's absolutely correct. So then what happens if the learning rate is going to be too big?
It depends on which algorithm we're using. Like if it's gradient descent or gradient, but in some cases it might turn out that it does not go to the minimum. Or
Yes, and actually it doesn't depend on the type of algorithm, because if you have an appropriate learning rate, you would probably either not converge, or because the learning rate is too big and you would travel across the surface, the feature surface, one way and another way, and you will not be able to make a step small enough to continue the converging process. And either or the learning rate may be too small, and then you will have another problem that you will make tiny little baby steps and you won't be converging fast enough. So generally, searching for an optimal learning rate is a great deal, especially in deep learning, because half of your success lies in good learning rate. Okay. We have discussed quite a lot. Okay, and we have something else here. We have regularization. So let's talk about this. What is it? And why do we need this even in the simplest algorithms that we use?
We use regularization to reduce the variance of our training model.
Well, in what case the regularization term is specifically important? When we talk about something some model which is very simple and very basic.
Like in linear regression, for example.
Yes, something like the linear regression. Okay, actually, we can have trouble when our data, our features are very correlated. And so it means that the feature matrix rank is actually smaller than we think. And that is why it can be irrevertible. And then we need this additional term to help us to deal with this. So there are two main regularization terms that you have probably seen so far. This is L2 and L1. So could you please tell me something about those terms, which are maybe you can even recall the formulas and some features that they have.
L1 basically sum up the absolute value of each coordinate of our estimator feature, and the L2 is just the Euclidean norm.
Yes, exactly. And okay, let's say we have a lot of outliers in our data, and those outliers, we think that those outliers are actually informative for us. Which kind of regularization would you use?
Those outliers are important.
Yes, they are important. We guess that the fact that they are somewhere distributed quite far away from the majority of our data may have some information. Even this fact.
You mean from L1 and L2? We have to choose one?
Yes.
I think the mix of both of them actually. The elastic net thing.
And why?
Like if you use both of them, the L1 removes the features that are not that are L1 removes the random noise, but the L2 will help to not overfit, I think.
Well, maybe yes. It is a good it is a good way to use them together. But okay, I was thinking about something else because I was trying to tell you that the L2 regularization gives more penalty for data which is far away. So for outliers, we have more penalty. If we make mistakes on the data which is distributed far away from the majority, so we get more penalty because it's square. I mean, we calculate the square distance. And L1, yes, it was absolutely correct. It removes the features which are not that important or give not that much impact to the general model. Okay, we're done. So the result is that the best learning rate would be 0.3 and something. And the best loss, and we used I guess log loss is 0.60 and something. So I guess we would move on to another one. Can you see the LightGBM notebook? Guys?
Yes.
Okay, great. So LightGBM LightGBM doesn't have that much functionality as Catboost does. Actually, I don't know why, but sometimes it's much more convenient to deal with this one because it just doesn't provide you thousands of ways to do something, and if you just need to create something fast and sweet, you can use this one. So as you can see, there are some data sets in this framework as well. Just split and make a classifier. It's very it looks very similar to scikit-learn and other stuff. Okay, so here we have a matrix, and if someone can calculate precision and recall using this matrix right now. Guys, do you know the formulas? Okay,
for accuracy,
not the accuracy, precision and recall. Okay, for precision, the formula is true positive divided by the sum of true positive and false positive. So what would be precision? How many true positives do we have?
True positive divided by true positive plus false
Positive.
false positive. False negative, I think.
It's for recall, and right now we're talking about precision.
Oh, we are talking about precision.
Yeah.
Yeah, precision is true positive divided by true positive plus false positive.
Yes. So what would be precision for this one?
This is precision.
Yes, and for in numbers for this heat map.
Once 60 plus add 60. Okay. 60 by 63. Did I get it wrong?
Actual negative. These are false positive. Yeah, 60 divided by 63.
63.
Yes.
Yeah.
And recall.
I think just one.
Positive divided by true positive plus false negative. Yes, it's one. Okay, so right now you have everything to calculate F1.
Sorry, did you say something?
You have everything to calculate if F1, so I'm waiting for you to calculate F1.
Okay. Precision was 60 by 63, right?
Yes, and the recall was
Recall is
1.
1. 60 by 63 divided by 60 by 63 plus 1. 123. 60 cancels out. 60 by 123 into 2. So 120 by 123, I think.
Okay, what would be the formula, first of all?
Precision into recall divided by precision plus recall, whole multiplied by 2.
Yes, it's correct. And in numbers you have
60 by 63 into 1 divided by 60 by 63 plus 1. Numerator you get 123 by 63. So 60 by 123 into 2. 120 by 123, I think.
Well, I guess I haven't calculated it myself. So the formula was correct. The main thing here is the formula. Okay. In many frameworks, you will see the same thing, that you can define some parameters by some kind of dictionary. And this is the most popular way to interact with some configuration for many frameworks in deep learning and machine learning. So it's just very common. Okay, so on test we have 0.95 and on train we have 0.98. Okay, let's talk about training, validation, and test scores, and what can we do to avoid overfitting to our data, and how can we see that during the training our model has overfitted. So first of all, we need to establish that the overfitting has started. So how do we do this?
Can you repeat? Sorry.
Okay, let's imagine that you are training some model. And you have to be sure that you are not overfitting to the data.
Its accuracy score will increase, but the training set accuracy will decrease. Oh no, its training set accuracy will
Yes.
increase. The one we didn't train it on will decrease.
Okay, and can we use something else except for accuracy score?
Maybe we don't know anything about the model. It's for any model, right?
Yeah, it's for any model. It's just the point is that you have chosen the accuracy score, but accuracy score can be a metric to evaluate the performance of the model, and it also can be a loss function. And in general, not all the metrics can be interpreted as a loss functions. So the best way, the most general answer would be that the loss function, the values of the loss for a training set would decrease, and for evaluation set, it would be increasing. And when you see the cross between the training and evaluation curve, it means that you are overfitting to your data. Okay. Okay, there are many possible there are many things that can cause overfitting. For example, the lack of data. So how can we work with this fact? What can we do to our data to avoid overfitting? Let's say we don't have enough data.
Well, we should use bugging or cross-validation to get more information about our validation set?
Well, you mean that we should use the part we essentially took for as a test set and well, not test, the validation set, and use it during training using cross validation. Okay, we can, but in most of cases, this is just about 20% of data, and it doesn't make any big difference. So how can we produce more data?
By bootstrapping?
Well, it doesn't make your data more different, and it actually won't help you with overfitting, because you would probably see the same data that you have seen earlier. So what can we
If
do?
it's an image, you can flip it, or
Yes, and okay, and what are the general what is the general name for any flips and other ways to?
augmentation.
Yes, you can augment your data, and it works very well. And let's say that we let's say we are making a credit scoring model, and for example, we have our own data set, and we also found something on Kaggle, which is very similar to our data. And can we use this to train our data? And how can we train on two data sets if we are not sure that one of them is of the best quality? So basically, the idea is that if we have our own data set, which is provided by some company we work in or something like this, we have some certain distribution of data in this data set. And if we find something, if we find some public data sets, we can't establish if the distribution of data in this data set is close to ours. So we just generally can see the features and maybe the data set we found is for a similar task, but still we are not quite sure. What can we do?
Like what can we do by changing the data set or the model?
We can make up some way to train the model on both data sets, but so how can we do this to make the best to have the best result? So maybe we can change the data set. So it's an open question. You can I'm here for your suggestions.
We can train on the best data set, and then we can just run the model on the second one and see how much they agree. If the accuracy is very high, then that should also be safe to train.
Okay, it's a good way. Any other ideas? maybe we can analyze the data set somehow. Okay,
Or
actually we can
give more weight to the original data, the one that's,
yes, we
and
can.
then just train it. I think it should be fine.
It may be fine, but it's maybe actually quite complicated to do. And there is the most common way to deal with such circumstances, that you first train on the public data set that you found somewhere, and then you fine tune to the data set you have for, I mean, the original data that you were trying to use at first. So that is why that is for model to learn some general dependencies from the data set that is not you cannot establish that it's quite it's 100% good for your task, and it would be the way to obtain the 100% best model you can. So you just take the general dependencies from this part, and then you fine tune to capture the more specific dependencies which are present in your data set. And you, of course, can make some visualizations and dataset analysis to establish whether the data sets are very different or not. And it's always recommended to do so, even if you are training the way I just described first, when you first use the data set that you are not quite sure about, and then your data set. Okay. Okay. And there are also some ways to prevent overfitting using the loss function, and we have discussed them today. What are those? So we have discussed regularization today. And this is also a way to avoid overfitting. Because somehow when you, well, not somehow, quite obvious when you use regularization terms, you you control the weights not to grow extremely not to grow extremely fast. Okay, so what would happen if the weight of your model would grow very, very fast, and what can it cause? Guys, this is the last question, and I will let you go, I promise.
If the weights grow very fast, our loss functions should penalize that and shouldn't see those, should converge to other minimum value.
Okay, in real life, if you in real life, if this happens, probably some machine learning library would say that the model hasn't converged. But what would happen if we consider it as a mathematical problem? So it's true, it won't converge. So what is the mechanism of this non-convergence situation?
Not sure about the question.
Okay,
Could you
when we
clarify?
have when you have very big weights, those weights make your model to step to respond to any feature very by making very big steps from one side to the other and so on. So that is why you can't converge. You're just let's say moving around some place you are trying to converge to, and not being able to get there because you're making two big steps, no matter how little the difference between values is. So this is the mechanic of non-convergence in this situation.
Oh, I
Okay,
see.
this
Or,
was the last question. So I guess I'm not quite sure, but I guess the rest of seminars I'm going to be your lecturer. So see you in 1 week.
I have one question.
Yeah.
These are seminars, right?
What?
These are seminars, right?
Yes.
We don't have lectures. Like, we only have these seminars. Could you please inform your team, please, about this problem?
You don't have any lectures at all?
Like the seminars that were conducted by Elisa, she like made it kind of lectures because we didn't have lectures. We only had these seminars on Fridays.
Okay. Okay, I will talk to her, and probably I can make those seminars half lectures if you wish. Okay, this
Would
explains a lot. Okay.
it would be like good if you could inform like your team, like girafe-ai, about this, because not having lectures is it's very not only inconvenient, but is very bad. Really.
Okay. Okay. I will tell the team. Okay. Next time we'll talk about the basics of deep learning. So see you next Friday, same time.
Thank you.
Thank you.
Goodbye.